solutions where we don't have like one solution that is provably correct and better than any other. So wicked problems, they don't really have a clear problem definitions, and solutions are either good or not good enough. And you often hear the term satisficing. Like this is problem, the solution is satisficing to that wicked problem. So you have multiple solutions that exist, but none are necessarily absolutely true or false. So like there is just the nature of what we're doing in this class is that there's going to be different ways of doing the same thing, but which of them is better or worse is really difficult to characterize. And so what you really have to think about is, does my solution satisfy the problem, and is it better maybe than some others, but is it generally, the most important question is, do you like help solve the problem? And the other thing about wicked problems is, like, if you have a mathematical like proof, you know you're done when you have proven the theorem. But in design solutions, you never know when you're done, right? It's always, you can always improve and make it better and make it more suitable for this explicit thing. So examples of not wicked, tame problems, and that doesn't mean that they're not hard. It just means they're not wicked in terms of not being absolutely testable. Things like mathematics, chess, or puzzles. Those have like unique solutions, and you know when you've arrived at the solution. And bridge design is clearly, for example, a wicked problem. And then here, you've probably seen this video of the Tacoma Narrows Bridge. Like that bridge was like just opened a couple of months prior to that incident here happening, and so clearly this is not a satisfying solution to the problem. Here, the engineers, when designing this bridge, forgot to account for the strong wind forces. And then, like the most amazing thing is this is actually a color video from the 1940s or so. You can see. You can see like how the cables here are moving, and then eventually here. Yeah. So it's hard to screw up this much with the visualization design. But of course, could be happening, not with that detrimental effects. Oh, one second, sorry. So, there are methods to help you design something. And so these will only be teasers. Like I could spend like a lecture on each of these methods, but I'll just give you a couple of hints on how to approach this. And I would actually recommend that you look at some of these methods and try to apply them for your project, especially for the proposal when you design them. Like you should probably not, like there's some that are targeted to eliciting user requirements, but you're likely not going to have users. So maybe that's not the right method, but there are some design methodologies in there that you could use. So one of the methods that I really like a lot is creativity workshop or creative visualization opportunity workshops. That's a method that has actually been developed at our lab by a student, Ethan Kirchner, who has just graduated. And the goal is more or less something like requirement engineering related to data visualization. And so the goal of running a creativity workshop is about generating design requirements, but also promoting creativity among like the visualization designers, but also the other stakeholders of a project. And so these creativity workshops, they give you like a rough framework of different activities that you could use to elicit these kinds of requirements. And things like wishful thinking. For example, a wishful thinking activity would be, let's suppose there were no computational constraints in your data analysis problem. What would you like to see? What would you like to do? And then you sit down, analysts, and like brainstorm on these kinds of questions and ideas. You do constraint removal, which is like similar to what I just said. you could do analogical reasoning that would usually be like showing people a variety of visualization solutions that are not necessarily tailored to their problem, but just to give them an overview of what is out there, and then have them come up with an analogy. How could they use this kind of visualization technique in their work? Storyboarding, and so on. And so Ethan has created this website that is actually quite useful because it lets you pick these different methods and explains how to run them. So you can click on, let's say, barrier removal here, and then you get a description of how barrier removal is supposed to work, what you need to do with it, which papers have used this before, so that you have some reference, and so on. So you can build your own workshop with that. And usually this takes between like 3 hours to like up to 2 days. And there's like many different methods here that you can use. And this creativity workshop turns out it can be somewhat uncomfortable initially for people who tend to be in this very narrow engineering mindset because there are some like let's say more creative techniques in there. But we've just run one of those. Like Jen actually just ran one of those last week, and we were like working with researchers and medical directors and analysts at ARUP, this like laboratory for blood samples, on developing like a visualization technique for their new like analysis pipeline. And so we had like 8 or 10 people in the room, and they spent 3 hours doing this workshop. And so you can see that they're like here coming up with ideas and concepts based on different categories. They're putting those on post-it notes. And we then, Jen afterwards, did some qualitative analysis of these concepts. There's some ranking activities in these workshops too, so that we can come up with like a set of very broad requirements and features for visualization tools. A much more general technique is parallel prototyping. And parallel prototyping is really something that I definitely encourage you to do when you design a visualization solution for your project. So I like this example here of what happens when you do serial development versus parallel development. In serial development, you start out with an idea, you sketch it, and then you continue to refine it. But by not forcing yourself to kind of think of new things, you tend to kind of like only do minor adjustments to your initial designs. But however, if you do like a really parallel design and force yourself to do 3 completely different solutions, then you will have an opportunity to actually take the best of all of these worlds. Or even if you just pick one, you will have a better sense of like this is actually a good solution compared to these others. So parallel prototyping, there's a lot of research on parallel prototyping. Here's like one paper cited that there's demonstratively like a benefit of using these parallel approaches. And there's like in design, it's like in graphic design, it's very common to force like graphic design students to do 5 or 6 or 7 design solutions in very short time. It can be exhausting, it can be challenging, but usually the rewards are worth it. Who's heard of paper prototypes as like a software user interface engineering methodology? Like 1 or 2 people. So like, what do you think? Like in a software, this is more general for software engineering, not just for visualization design. But one problem that we have as people who build software is that to show something, to give a demonstration of a tool, we need to have something that's fairly high fidelity already to like simulate interaction and so on. At least if you want to show a real system. The problem with that is that once you have built such a real system, there's a lot of like assumptions by your users that like asking you to completely change something is actually not very polite. And also you yourself might be hesitant and might prefer the way you've already implemented it and might think, well, I could do that, but is it really necessary? And so there goes a lot of effort goes into creating a high fidelity prototype. And the opposite of having these high fidelity prototypes is having like the absolute lowest fidelity prototypes that you could imagine. And those are paper prototypes. And so here in paper prototypes, you really sketch on paper an interface. And then, for example, if you have a dialog button or something like that, you would have different sheets that you have prepared for when the user clicks here, you show your test user a new paper or new state of the interface. So you kind of like walk them through a variety of scenarios just on paper. And there's like ample research in the HCI community that shows that these paper prototypes lead people to be much more critical of your interfaces. Yeah.
So it's just like the 90s version of wireframe?
Yes. Wireframing is very similar to that. And you can also do this, of course, with like slide decks or anything like that. Yeah. However, like there's also a theory that wireframing itself like looks much more like the real product, right? So as soon as you go into the digital world, people have the assumption that it's much more finished than it really is. And so this is, I think, what this paper is about, this 2011 paper comparing these methods. And there is like evidence that these like low fidelity prototypes actually have benefits to creativity. A methodology that has been used also in teaching visualization, but is kind of useful for a context like your project, is the 5 design sheet methodology. So this is really tailored to visualization design for both industry and classroom use, and it really gives you, like essentially forces you into a structured design process. And so it's like 5 sheets, obviously, but 3 types of sheets. So sheet 1 is about ideation, filtering, categorizing, combining, and refining, and then having like listing questions. And then you have 3 parallel designs. Like 2, 3, and 4 are sheets where you're supposed to do the same thing with different approaches. And there you have these categories: layout, information, operations, focus, partitioning, and then a discussion of those. And then the 5th sheet is supposed where you converge on like the solutions that you created in sheet 2 to 4, where you converge, are you supposed to converge in sheet 5. And so FDS.design has these detailed design sheets, and that's something that you could definitely try out for your project. And then, of course, you could also put this in your process book. Visit cards are, again, methodology that has been used in classes like this, where there's cards of different types that support you in reasoning about the design space that's out there. There's like domain cards, there's like some perceptual principles, like here Gestalt principles, and these inspiration cards. There's abstract cards and there's layout cards. And there's like a card game where you like find, for any questions that you would have, you find one of the possible solutions for that to kind of like be sure that you explore a broad spectrum of possibilities. And so that's one thing that I think has been most used in the context of teaching. And of course there's other methods. Like the classical way is interviews, observations, like conducting interviews with potential users. There's also things like lean canvas that are in that space. You can do some qualitative analysis on like whatever interviews you do. Another like common method in HCI is personas. So when you develop a piece of software, you think about who are my potential users, and then you create one representative class for each of your potential users. So that could be like your frontline analyst versus some like decision maker. They are supposed to use the same software. The frontline analyst would do some like prep for the decision maker. So you, by explicitly creating those personas, you make sure that you design for all of those different use cases. Data sketches, where you like simply create lots of sketches with data, or any like you can also code to explore designs, of course. So all of these are like these more creative methods. And next I want to talk about evaluation. So once I've built something, how do I know that it's better than something else? So, any ideas of how I could know that A is better than B?
I think you could poll some people that have never seen it before and just get some feedback on what's more intuitive or.
Yeah. So you could do like demonstrate it to people and then give them questions, an interview, or even like a questionnaire, ask them to rank, or anything like that. Other ideas?
I was gonna say, like, could you use Mechanical Turk and like track the time that, you know, try and extract data from that to see kind of how quickly, and then have them answer questions?
Definitely. You could use any kind of like platform, either lab study or Mechanical Turk, to set up two different cases, two different scenarios, compare completion time, correctness, other log information, and then like basically have a quantitative answer to a specific question.
I was going to say, if this is important to you, you can measure the number of clicks it takes to get to whatever your principal goal is.
Yeah.
Between the three designs.
So you could do some instrumentation, some like log file analysis, and then evaluate like how many clicks does it take to achieve a certain goal. Any other ideas? So what do you think about, would you be convinced if I showed, like, evaluated something by just demonstrating that it solves a problem? So that's the method that's called case study. So let's look at this in a little bit more structured way. So the role of evaluation and validation is, like, our goal is A, to avoid ineffective solutions, and B, to justify the solutions that we made. And so there's a couple of dimensions to this. And I think that's very important to distinguish, because the two answers, or the three answers that we got, are on this very different end of a broad spectrum. So we have things that are really more perception-based, like, is length a better visual variable than, let's say, saturation? Or is the area of a circle misperceived compared to the area of a square? These are questions that are very, very basic, right? So we can actually run a very controlled experiment, and they are actually reproduce excellent across diverse populations, these kinds of questions. However, if you have a visualization system, let's say I build a complex tool to solve a complex domain task, how do I like make such a comparison effectively? And it's real. The answer actually is it's probably not possible to make this a really like unbiased quantitative comparison. So we'll talk about this a little bit more. So is my visualization system any good? Is quite a different question from is angle a better visual variable than position, right? And then another thing that you have to worry about is is my system unique, or can I make a comparison? So can I easily compare my visualization to others? For example, if I have created a new node link layout algorithm for graphs, I can, like, there's many other node link layout algorithms out there. So I can devise an experiment that compares them. But if I've built, like, again, a system that is very unique to a specific domain, I might not have something to easily compare it to. So I have a one-of-a-kind system. And another aspect here is not testing for, like, whether something is better or worse. You're testing for usability. And usability testing is quite different from evaluating something, right? You're testing whether it's usable in the current form it is, but you're not comparing it to anything else. And all of those are very useful for different scenarios. So here is an example. It's a paper that I wrote with some colleagues in 2011. So here, I showed this a while ago. So the question that we try to answer here is, are these visual links that show connections between those highlights, are they better compared, like, are these links here better than these highlights here, or these, like, context-preserving links better than any of those? And so our question here was, can you find all of the targets faster, and do people do that more correctly? These kinds of questions, what do you think would be like a good study, a good experimental setup for that?
Maybe like eye tracking.
Yeah, eye tracking. Eye tracking implies like a very formal setup, right? A lab study where I have complete control over the environment. And so that's exactly what we did. We did an eye tracking study here, and we did a performance analysis of task completion time and correctness. And so we had hypothesis, basically said visual links lead to a better performance, are faster than conventional highlights. We had a second hypothesis, context-preserving links do not have a negative impact on correctness. And these were hypotheses. We did a controlled laboratory experiment. We ran like I forgot the number of people, but like 30 or 60 people through that experiment. Then we did some statistical analysis, and we could actually show with like a high degree of certainty that visual links help speed up the process of finding all the targets, and visual links lead to higher correctness. And so we were happy about that. However, we did not actually, we did not have a hypothesis that we could really test in detail whether this or this is better, right? Because that's a much more subtle question. So, for example, the point of this technique here was that it doesn't include any text. But how do you test that, right? And so there we kind of tried to get at this question with like, what did you prefer, or did you think this was useful, and so on. So the evidence for like this being better than that is much weaker than the evidence for like any visual link being better than no visual link. But we also did the eye tracking component here was we tried to understand like how did people actually do that, and so we ran this on an eye tracker, and like these are gaze plots from all of these subjects overlaid to each other, and you see that this is basically fairly chaotic. There's no clear structure to it. It's very dispersed across the whole display. Whereas you see that in those two cases here, it's much narrower. So people don't actually spend time like looking at these corners here or any of those corners here because they don't see a visual link going there. So we have like some additional evidence of that these visual links really make you focus on certain regions of the screen. And you can actually like use these eye tracking data to like make more quantitative judgments too. You can define, for example, regions of interest, and then like quantify how frequently do people look at these regions, and so on. An example again from one of our papers that's on the completely different end is this genealogy visualization tool that we developed together with the Department of Psychiatry. And so there, this is like a unique system that solves a unique problem of studying like these large family structures and kind of like trying to understand suicide and genetic cause of suicide. And so the evaluation here was a case study. And so what the case study means is that the domain expert actually did an analysis with it and then demonstrated that she could find something that she couldn't find otherwise, that this tool was actually useful for her to discover something new. And the best alternative tool that they had before was this here. And that's like a general purpose genealogy drawing tool, but that doesn't scale to the kinds of family trees that they need to explore, and they can't look at so many attributes. So there isn't really much sense in running a comparative study. Is A faster than B if A simply cannot get the job done at all? And so therefore you use something like a case study to justify your design. So like more broadly, evaluation methods are controlled experiments, like we talked about crowdsourcing, laboratory experiments. Interviews and questionnaires can either be unstructured or structured or semi-structured. Interviews and questionnaires can also be used in formative work, as we saw earlier. Then we can do field observations and lab observations where we do some, let's say, video recording or audio recording and then a post-hoc analysis of the video. We can classify or code user behavior. We can classify or code logs, speech, gestures. We can do log analysis, and we can measure algorithmic performances. And so, as you can see, this is quite a spectrum again. There's also heuristic evaluation. Here we judge the compliance with some recognized metrics or usability methods. So like a classical example for heuristic evaluation is graph, like node link layouts, because we, like in node-link layouts, we'll have a lecture on this stuff, but you can kind of come up with criteria that people generally agree upon are beneficial. Like, for example, having all links of the same length, not having many crossings, not having links that are bent or anything like that. And so we agree on these metrics that are useful for a system, and then I can heuristically evaluate whether my system like outperforms another system. Usability testing is, for example, thinking aloud tests. Who's heard of thinking aloud tests? Yeah, 2 or 3 people. So thinking aloud tests are not an evaluation method, they're a usability testing method. And so in a thinking aloud test, you sit somebody in front of a user interface, and you ask them to achieve a task, but you ask them to articulate their thought process. And so by then recording that and coding that, you get an understanding of the internal processes of a human user when they're using an interface. And that's been quite helpful in many cases to identify usability problems. Of course, you could make an argument that by having to articulate it, I actually don't articulate every thought, and it kind of makes this whole process a little bit tedious and maybe not completely ecologically valid, but still, it's a useful method. Who's heard of Wizard of Oz experiments? One person. So Wizard of Oz is an interesting concept. It's like sometimes you have an idea, but realizing it would be quite complicated. And so you actually completely fake it by simply, like, for example, you say, I have a prediction algorithm for any like kind of scatter plot that you draw, I can draw the perfect regression line or something like that. And the system, like implementing that would be like effort. And so instead of actually implementing this, you have a human behind the scenes hide and do the task that the user expects the system to do. And by that, you can fake some advanced functionalities, like essentially fake artificial intelligence by using human intelligence to test out a hypothetical system. And there's papers out there in visualization that are nothing but a Wizard of Oz study. So for example, one paper that I really liked is that evaluated how you could use sketching to define visualization techniques. And so what they had like a whiteboard like this, or actually a smartboard, and they had somebody draw like a line chart, and then the system recognized, oh, are you trying to do a line chart and show the line chart? But there was no system. It was just a human looking at your sketch and like making their own best guess of what you could mean. And by that, they could demonstrate that these sketching interfaces to specify like visualization techniques are actually useful. We talked about eye tracker evaluation. Another way of doing it is expert evaluation. I think that's also fairly common in industry practice, where you have like some expert in the domain walk through your interface and try to identify problems. Because like experts are unlike novice users, right? There's a lot of skill to designing visualizations or more generally user interfaces that can be learned, and if you get an expert to review your system, that can be useful. Specifically for visualization, there's a technique that's called insight-based evaluation. And insight-based evaluation essentially tries, like, really the question when we build the user interface is, can people learn something new with it, a visualization interface? And insight-based evaluation tries to quantify these like mid-level insights. So like, I've discovered an outlier, or I can see that there is an interesting like pattern shared between those two items. And these are kind of like these mid-level insights. And that methodology codes those and then tries to quantify these more complex processes so that it can say, my user interface generates like 150 insights per minute versus your user interface only generates 80 insights per minute. And then we talked about case studies before when we talked about this genealogy project. So like usually when you want to make some like judgment, it's going to be in some way quantitative. But there are subjective and objective quantitative metrics. So objective metrics are things like task completion time, errors, either number of percent of tasks completed, ratio of success to failures, number of repetitions, number of commands used, number of failed commands, heart rate, sweat, or like any brain pattern or anything like that that is that you can measure, or the number of insights. Whereas subjective metrics are where you ask users about their opinions, their ratings, their rankings, their satisfaction, their subjective performance, their ease of use, intuitiveness, judgment, and comments and feedbacks. And you can make all of those also into quantitative data, right? Because like when we run this like a survey, we get people's judgment, subjective metrics, but we still do statistics on them. So both are quantitative or can be quantified, let's say, but there's a difference between the subjective and objective metrics. On a higher level, we have quantitative versus qualitative evaluation. And quantitative evaluation is really about objective metrics and measurements and using numbers and statistics for interpreting data, whereas qualitative methods is like makes use of subjective metrics, and it's really about a description of situations, events, people, interactions, observed behaviors, use of direct quotations, and so on. And it's focused really on understanding how people make meaning of an experience compared to like these hard numerical facts. So anybody want to think a little bit about pros and cons between these methods? Which one would you trust more?
Qualitative a little bit, since qualitative is kind of that, in a vacuum, this works perfectly.
Yeah, so you're bringing up an important point that I want to get to, ecological validity. Like in the vacuum, this works perfectly. And that's usually the trade-off that you have to worry about when you run an experiment like this. Are my results valid for this very narrow, well-controlled scenario, or is my scenario representative of a real-world problem? So we have this distinction between internal and external validity. Internal validity is high when tested under controlled lab conditions. So we can absolutely be sure that the observed effects are due to the test conditions and not due to some random factor. External validity is when the interface is tested in the field, and that tells you that the results are actually valid in the real world. So for example, if I have like a handheld device that helps me explore a museum and I actually test this in a museum, then I know it works for that scenario. But there are many confounding factors that can influence your test in this case, right? It could be like how the museum, the layout of the floor plan is structured, right? You can't really completely control that. So whenever you do something in the real world, there are usually a lot of confounding factors. So there's usually a trade-off between internal and external validity. So the more akin to real-world situation, the more the experiment is susceptible to uncontrolled sources of variation. So you have less certainty that what you're actually finding is because of the thing that you're testing. But on the other hand, you have more certainty that it actually matters in the real world. And so there's this complex trade-off to be made here. And so we talked about this, but this is just a recap. The scope of evaluation is really broad. We can start in the pre-design stage, in the design stage, in the prototype stage, in the deployment stage, and for a redesign. I'm not going to go into this again. So, at least in the visualization research community, which is like, compared to, let's say, like vision sciences, is like more about like inventions and engineering, less than about discoveries and like pure, absolute hard insights. It's really like, at least the sentiment of a fair number of people is that the added value of a visualization solution that you propose as a researcher should be obvious. And so I'd like to quote Jaart van Wijk here, who is like a well-known researcher from the Netherlands, and he gave a capstone talk, and he said, develop new methods or interfaces of software that are so awesome, cool, impressive, compelling, fascinating, and exciting that your reviewers, your colleagues, and your users are totally convinced just by looking at your work and some examples, and that you don't actually need to show any evidence that supports your claims. Of course, that's a high bar and it's an extreme position, but it's still an interesting take on this whole problem, and I think that there's a lot of truth to that. So if you find these kinds of things, these evaluation methodologies and so on useful, there's a fair amount of like lectures on this. There's we have, like as I mentioned in the beginning of this class, we have a new degree, the human-centered computing degree, and in that human-centered computing degree are a fair number of classes that are in this space. Specifically, the HCI course, which is taught in the fall, and the advanced HCI course in the spring, they will go into these methods. There is the Ed Psychology class, which is required in this degree program. They introduce statistics and research design. There's also a product design and development class. There's an ethnographic methods class. There's an introduction to research design in Ed Psychology. And so, like, there is so much more to talk about here, but this was really just meant to be a bit of a primer. Okay. So that brings me to tabular data for today. So in a second, I'll get you guys to do something. So as I already said today, the second half of this lecture will be a lot about how do we actually encode the data. How do we actually encode these different types of data? And so we'll be having like 2 lectures on tables, 2 lectures on network and trees. We will not be talking about fields. That's the course on scientific visualization that will be offered in the spring. We'll be talking about geometry in terms of maps. And we're talking about clusters, sets, lists, and also text in some of the future lectures. But today, and also on Thursday, and probably, like I'm assuming that I'm not going to finish even on Thursday, we'll talk about tables because it's such a big topic and a good introduction into the specific techniques. Okay, so first, an exercise for you guys. I would like you to sketch 2 ways to visualize each of those tables. And there's not more that I have to say about this. I just want you to think about, are these tables exactly the same to visualize, or do you have different methods that you would do? And I'll give you 5 minutes to do this. Okay, so any observations about this exercise? Exactly. So we have very different things. We have like a heterogeneous table. Every column has a completely different meaning, a completely different data type, and a completely different scale. So what does it mean for your visualization designs?
You can use more channels or more different marks.
Yeah, so you can basically solve the problem on the right by just color coding the cells, right? And you don't even need to repeat the beats per minute, but this is like the pulse of a person or something like that. You can just say T1, 90, T2, 130, and T3, 150, and it's ppm for every one of those columns. But then here on the left, you have to label each column. You probably should also use some kind of like channel that makes sure that everybody gets that they're distinct, that they're not identical. So that could be just like a variation in color if you use bar charts, for example. You also have categorical values here, which you would probably encode completely different. So those two are tables of the same kind of if you look at them initially, of the same kind of complexity, but you need to take very different approaches to them. So this is our textbook description of how I could actually encode tabular data. So first, you can just express values without considering any keys, or then you could separate, order, align regions by a combination of individual keys. Then we have these layout operations. If we use some axes, we could use either rectilinear or parallel or radial grids, and then we have layout options. And so we'll talk about all of these today and in the next lecture. And just recall that, as you will see today, that most of the channels that we're actually using for numerical data visualization, at least, are these like high-level magnitude channels and the high-level categorical channels, especially position, length. We'll be using color, luminance, and saturations, and some other examples today too. And then, of course, the semantics of a table matter. So when we arrange tabular data, we have to choose which attributes are keys and which attributes are values. And so let me give you, well, first I want to talk about the scale. So one thing like we talked about in the beginning with this example, that the type, like how complex the type of a table is matters in terms of your choices of visualization, but also the scale matters. And so there's a couple of different approaches depending on whether you have normal or really high dimensional tables. So for example, if you have about 50 dimensions, there are visualization techniques out there that can handle like a tabular data visualization with 50 dimensions. But if you have 1,000 dimensions in your data set, you're likely not going to find a great visualization technique that does that. But we can still do that by using some analytical methods. And we'll talk more about, like I'll have a dedicated lecture on clustering, aggregation, and these kinds of things. In terms of records, usually like records are more homogeneous. So we can usually show up to 1,000 records in a tabular visualization if I choose the right one. But if I have way more than 10,000 records, again, I need some kind of like analytical methods or at least interaction. I probably need an interaction at 1,000 too. And then, as we talked about at the beginning, homogeneity makes a big difference. Is it the same data type? Is it of the same scales? If you can say, yes, it's the same data type, yes, it's on the same scale, I can create a very compact encoding. And so I can probably do these 50 by 1,000 easily. I can probably do even like 1,000 by 1,000 if I have exactly the same data type and the same scales. Yeah, so this is what the example was about. And so I kind of like came up with this classification of these like major types of visualization based on their analytical needs. So on the left here we have scatterplot matrices and parallel coordinates, which are techniques that don't need you to use any smart algorithms or any machine learning or anything like that. You can just visualize your raw data with them. And bar charts and other stuff is in that category. That doesn't mean that you cannot use these methods to make them better, but by design you don't necessarily have to. In the middle here are these pixel-based visualizations, heat maps. They are in the middle because even though the representation here doesn't obviously use some algorithmic component, they are pretty useless if you don't cluster them. You kind of need some smart algorithm to show you patterns that you can then parse as a human. And on the far extreme are things like projection methods, where you have a very strong analytical component, things like multidimensional scaling, principal component analysis, where I then take these derived measures and visualize these derived measures, maybe their properties, instead of visualizing the raw data. And so multidimensional scaling in PCA, I'm not saying that it always works well, but conceptually it can handle an arbitrarily large number of dimensions. So the simplest example now is to express values in the tabular dataset without using any keys. And this is basically a complicated way of saying you can draw a scatter plot. And so a scatter plot, what I mean by no keys is that, if you think of bar charts and we have countries here, you would have let's say USA, Canada, Mexico, and so on. Here you don't have any keys, you simply show one attribute versus the other attribute and plot these items along here. And in this case we've done a couple of other things like encoded by size and so on, similar to what your homework is about. When we talked about regression a little bit, when we talked about some design guidelines, regression lines can be quite useful, but also people are decent at doing that. And this is just a comic, like an XKCD that I like. Don't trust regression lines when it's harder to guess the direction of the correlation from the scatterplot than to find new constellations in it. So mathematically, you would use least squares to minimize the sum of the squares of the errors to find a regression line, a linear regression line, or you could have really high order regression approaches here. But remember that regression lines are a summary statistic and therefore are necessarily not complete, right? So this is Anscombe's Quartet, and you can see that the regression line here corresponds only roughly to what you expect in the first case, but not in the other cases. When I want to encode one key attribute, I basically end up with a bar chart. And then I have a couple of choices to make, or bar chart or line chart. I can order separate and aligned. So these are separated and aligned, but the ordering here is interesting. So when I have, here I have an alphabetical ordering based on keys. On the right I have an ordering based on the values. And so either is possible. And of course in temporal data, you do want to not order by anything other than time. If I want to encode multiple key attributes, I get into this matrices or volumes or recursive subdivision examples. So here is a simple visualization where I use two different keys for a stacked bar chart, like a recursive subdivision. So here I have keys. This is a Titanic data set that we'll be revisiting a couple of times. So Titanic, as you know, the ship where a lot of people perished, but it turns out that there was some, not every group of passengers or people on the boat was equally likely to die. Women who traveled in first class had actually a pretty high chance of surviving the disaster, whereas male staff probably died. And so this is this data set that kind of tells you, in red are the people who died, in blue are the people who survived, and then you have class as your as our primary key that we use to facet by. And so you can see that in first class, there's actually more people who survived than died, whereas in third class, there's a lot more people that died than survived. And the comparison here is, on the left I have an absolute value, so it kind of shows us an overall like impact and gives us a head count. But if you want to look at the proportions, we see it is in this proportional value chart on the right. We see the differences that we actually care about here. The differences between the classes much better. And this is related to the whole like faceting and grouping that we talked about when we talked about trellis plots. But this is from a figure by Mark Stride and Neil Scalenport. This is a figure from a paper by them where they discuss different ways of using these bar charts. And so, like, you could use a bar chart, you could use a stacked bar chart, you could use a layered bar chart, or you could use a group bar chart. And so which one you use always depends, of course, on your question. So if the overall sum of these items is important, or of these groups is important, then you would use a stacked bar chart. If you really want to compare the items within each other primarily, you would use a layered bar chart. If you want to compare the items within these categories, you would use a group bar chart. And so these are kind of like your options to using keys here to create different types of bar charts. We can use a stacked area chart, or alternatively, we can use a 100% stacked area chart. And those two have actually like quite different, they can answer quite different tasks. So I actually like this example here. So this is a market share, and it's not really important what this is, but let's say I have a yellow, a green, and a blue product. Can anybody describe what they're seeing in this chart?
Changing percentage market share over quarters.
Yeah, but could you be explicit? Like green is getting...
So green has a relatively constant share of the market, while blue is increasing and yellow is decreasing.
Okay, and so let's hone in on green. Everybody agree that it's relatively constant? It decreases is what I hear. Like, who would agree that it decreases? Who would agree? Who would think that it increases? Who thinks it's roughly the same? Okay, so you're like the people who think it decreased are falling back victim to a common perceptual problem with these stacked area charts. So the thing is that you are actually judging the distance from here to here and not the distance from here to here. So if we plot the same chart as a line chart, yellow and blue was quite obvious, right? But that green is slightly increasing was really missed. And again, this is because you're like, instead of judging the distance from here to here, you're judging the distance from here to here. And so these stacked area charts can be kind of tricky to do. And here is an example. Like this is weapon sales in there's miscellaneous weapons, revolvers, shotguns, pistols, and rifles. Either in stacked bar charts or stacked area charts. What is the most striking trend in here? So overall, we see that there is like quite a significant peak towards the end, right? But if we actually break this out as a line chart, we can see that one of those is the pistols here are really off, like on a trajectory that's quite different from everything else. So they like around 2004, they were kind of like a low share or low numbers, and then suddenly they skyrocketed. And that's of course something that's much easier to spot in this line chart as compared to the stacked area charts. Of course, the overall trend is more difficult to see here. So again, as usual, it depends on your topics. Tabular grid or matrix-based representations are the next topic that I want to talk about. And tabular representations are basically like a spreadsheet. Here, each variable is in its own column, and then you use visual encodings to make it scalable. And so the classic tabular visual encoding is the table lengths. And I want to show a short video here. let's just go to. Why are there so many Apple TVs? Bedroom Apple TVs. Right. Okay. I'm ready to give up on this. Anyways, like I'll just tell the story. So this here, like as you see, this is from the 90s. But this is about baseball players, baseball statistics, and so you have all the baseball players and Major League Baseball in this one big table. And as you can imagine, there's a lot of people, and therefore you can't really just treat this as a spreadsheet. And so what they do is they use like a lens to focus on certain people that you can read their labels, but then use graphical abstractions like these bars here to show how frequently, like where they at bat or any other dimensions along these lines. And you have like these numerical encodings on the one side, and then you have also categorical encoding. And as you can imagine, this is particularly useful if you can use interaction. And so they're showing some things in here. Like here, for example, they have like a gesture for sorting, and now they're sorting by their career home runs. And so you can look at the people at the very top, how do they relate to each other. And then you can also sort, like see that career at bats, like this was not career home runs, but career at bats corresponds to career hits. But there are some people that don't actually follow the pattern and are a little bit of an outlier. These are the kinds of interesting cases. So I'll keep this short since the audio doesn't work. Also because I can show you like a more modern version of a tool like this. Yeah, this is it. So this is a technique, I think I've shown this before, but it's important to show it in this context here. This is a technique that we built that takes some of these ideas, but does also a couple of other things different. So here I'm again like looking at soccer players, and the thing is that I can like sort here by different aspects. So for example, here I'm sorting by age, by height, but I can also sort, like here we have a visualization of their goals over time, and we can also sort by the number of goals. And if I do that, we can see that the people that you would expect to be here, like Cristiano Ronaldo, Lionel Messi, and Zlatan Ibrahimovic, are at the very top of this list. And so that's a very, like, let's say, graphical way of exploring a table. I can also create groupings here. So I can say, what are the wingers? Like, for example, here I like have the center forwards. But if I want to ask the question, what are the wingers that are doing well with their goals? You can see actually Cristiano Ronaldo and Lionel Messi are both wingers. So I can use these aggregation methods to group by any either bin, numerical, or categorical variable to explore a large table like this. I'll talk more about how I can use this for like multifaceted ranking a little bit later. Another technique where I would use audio is Birdifier, so I'll hope that I can fix this next time, and I'll skip over this for now. Here is an interesting piece that's like multiple line charts. If I use like time series in such a table structure, like the problem with time series is that they can be, like, to see the differences, you need a fair amount of space. And so the interesting idea from this paper here, Sizing the Horizon, is that you can actually take a line chart like this and make it more compact. So here we have like the original line chart. We can see this oscillates between negative and positive. And so what they do is they like first create two bins, negative and positive, and then they divide it one more time between like in the middle here. And you see that these dark blue segments here are like the peaks. The red blue are the like draws at the bottom. And then they kind of like instead of showing the peaks extend like this, they move them back in. So this is what you get here. And then you can either like mirror the negative values and then have this very compact layout, or you can offset the negative values. And now this is a much more compact representation that you can use to show a large number of time series in such a tabular layout. And this paper also contains a study that shows that people are actually quite good at reading those. And so next time, I'll continue with the table lecture. I'll make sure that my audio works before I start the lecture. And I'll see you on Thursday.
Hypothetically, you want to do nothing.